Have you ever taken a photo, a really big, high-quality one, and wondered how it gets shrunk down to a tiny file you can email, and it still looks amazing? It honestly feels like some kind of digital magic. Well, today, we're going to pull back the curtain on that trick. It's not magic, it's math. And it's one of the most beautiful ideas in all of science. So, let's kick things off with a problem we've all had. You snap this perfect picture, but the file size is just massive. You try to upload it, email it, or just save space on your phone, and it's a huge pain. This is exactly the problem that JPEG compression was designed to solve.
And this really is the big question, isn't it? How can we literally throw away most of the information in a picture and our eyes just don't really notice? The secret isn't about just deleting random bits of data. It's about fundamentally changing how we look at an image in the first place.
I mean, just look at the numbers here. We are often throwing away 90% or even more of the original data. And yet, the compressed version looks pretty much the same. How is that possible? Well, the secret isn't just in the computer. It's an incredible insight into how our own eyes and brains perceive the world. To get it, we have to stop thinking about an image as a grid of pixels. Instead of a grid of pixels, we need to start seeing images as a collection of waves. Now, I know that sounds a little weird, but trust me, this is the key that unlocks the entire thing. The whole compression trick hinges on this one single idea. We have to stop looking at an image in terms of space, a grid of little colored squares. Instead, we're going to learn how to see that same image in terms of frequency, as a big, messy combination of different waves all added together. And this idea is absolutely fundamental. It turns out that any signal, and I mean any signal, whether it's the sound coming from a guitar, a radio wave, or yes, the light and dark parts of a photograph, can be perfectly built by adding up a bunch of simple, pure waves. These are called sinusoids. This new way of seeing things is called the frequency domain. And the best way to think about it is like this. Your image isn't the finished cake. It's the recipe card. And on that card, it lists all the ingredients, which are our simple waves, and it tells you exactly how much of each one you need to mix in to create the final picture. And here's the intuition behind it. You start with a really simple, slow-moving wave. This represents the big, broad, smooth changes in brightness across your image. Then you start adding in faster waves, and these faster waves create finer and finer details. If you just keep adding enough waves, all with different speeds and different strengths, you can perfectly recreate any signal you want, no matter how complex it looks. Okay, so if our image is really just a bunch of waves all mixed together, how in the world do we unmix it to see that recipe? Well, for that, you need a very special mathematical tool. And that tool is the legendary Fourier Transform. You can think of it as a kind of universal translator. It takes our image, which is written in the language of pixels, and it flawlessly translates it into the language of frequencies. So what the Fourier Transform gives us at the end is basically a complete inventory. It hands us a list, and for every possible frequency, from the super slow ones to the super fast ones, it tells us exactly how strong that wave is in our original picture. It's the complete recipe. But, this brings us to another little problem. Just knowing that a wave exists, or even how fast it is, isn't quite enough information. To rebuild it perfectly on the other side, we actually need two pieces of information for every single wave. So first, we need its magnitude. Think of this as the wave's strength, or how tall it is. A wave with a big magnitude is a really important ingredient in the image. And second, we need its phase. And that's just a fancy word for where the wave starts in its up and down cycle. So for every single frequency, how can we possibly store two different pieces of information? Well, the answer is just so clever. It comes from this beautiful corner of mathematics that feels like it was practically invented for this exact problem. Think about it. We need one single thing, one mathematical package that can hold two separate numbers at the same time, the magnitude and the phase. A normal number, like 7 or negative 3.5, can only hold one value. So we need a special kind of number that gives us a 2-for-1 deal. And that special package is the complex number. Yep, you might remember these from math class. They're the ones with two components, a real part and an imaginary part. And because they have those two built-in slots, they're the absolute perfect container to hold our two pieces of wave data.
So, for every frequency in our image, the Fourier transform gives us back one single complex number. And that one number is the key. By combining its real and imaginary parts in a clever way, we can perfectly calculate both the wave's strength and its starting point. But to see why this works, we need to know what those real and imaginary parts actually stand for. And this is where it all just clicks into place. Those abstract-sounding names, real and imaginary, they actually correspond to two very real, very fundamental types of waves.
Here's the connection. The real part of that complex number tells us how much of a cosine wave we need to use. That's a perfectly symmetrical wave. And the imaginary part tells us how much of a sine wave to use, which is an antisymmetrical wave. So by mixing just the right amounts of these two super simple, fundamental shapes, you can create any wave you could possibly want, with any strength and any starting point you need. Okay, let's tie this all together. We started with a picture, we used the Fourier transform to translate it into a recipe of waves, and we stored that whole recipe as a big list of complex numbers. So, how does this actually help us shrink the file? This is the punchline, and it's all about human biology. See, our eyes are incredible, but they're not perfect. We are super sensitive to the big, slow waves, the low frequencies that define the overall shapes in an image. But we are not nearly as good at seeing the tiny, really fast waves, the high frequencies that represent all the super fine, grainy detail. So once we have the image translated into its frequency recipe, we can just throw away the ingredients our eyes don't care about anyway. So the whole process looks like this. First, the Fourier transform breaks the image down into its wave recipe. Then the compression algorithm comes in and acts like a ruthless editor. It looks at all the high-frequency waves, those tiny details, and it just deletes them, throws them out. Now, this is what we call lossy compression, because that data is gone forever. But because we were so clever about what we threw away, targeting only the information our eyes don't really miss, the visual difference is tiny. And that's the secret, a much smaller file that still looks amazing.
It is such a powerful idea. And this isn't just for JPEGs. This is used in audio processing, in MRI machines, in astronomy. It really makes you wonder, right? If we can understand a simple photograph so much better just by translating it into the language of frequencies, what other parts of our world could we understand better if we could just find a way to see their hidden frequency recipes?